All right, so welcome again. Last time we started discussing quotient topology for two spaces x and y and a surjective map from x to y. We say that P is a quotient map if the following happens: a subset in y will be open if and only if its inverse image is open in X. So if this is the case, then we call P a quotient map. And then we saw that putting an equivalence relation on a set X is the same thing as writing down a function from X to another set, but as surjective function. So given a relation, we consider the set of equivalence classes, call it Y, and then we have a map from X to Y sending a point to its equivalence class. And conversely, if we have a surjection, then using this surjection, we can define an equivalence class on X, where two elements of X are related if and only if they have the same images under P. And then these two constructions, determines each other. In other words, if you start with a surjective map and write down the equivalence relation obtained this way, and then if you then write down the surjective map determined by this equivalence relation, you will get back to the original surjective map, and vice versa. If you start with an equivalence relation, then obtain a surjective map, and then another equivalence relation from that surjective map, you will see that the two equivalence relations will be the same. And okay, we had this construction. Suppose we have a surjection from x to y, f, and we know that this surjection can be seen as the y can be seen as the set of equivalence classes of an equivalence relation on x. And if we are given a function from x to z, the question is, can we find a function from y to z so that the composition f and g, f and h is equal to g? So okay, maybe we should do it here. The answer is that there is such h if and only if the function g is constant on each equivalence class. Okay, this is easily seen. And then we consider topological version of this. And before that, we did the following construction. If X has a topology, say tau, then the strongest topology on Y, the set of equivalence classes, so that this map, which sends every element of X to its equivalence class, is continuous, is called the quotient topology on Y. Okay. So if you have a surjective map, then you can put a topology on the image set Y using the topology on X, where you declare a subset U of Y open if and only if its inverse image is open. So that's called the quotient topology. And here comes the important result. Okay, so let F x to y be a quotient uh, map of topological spaces. Okay, so y is a quotient of x and y. Let uh, let g from x to y be any map uh, from x to a topological space, another topological space z. Then there is a continuous map h from y to z, so that h composition f is equal to g if and only if and only if uh, uh, g is constant on the fibers of f. So what does this mean? It means the following. So I have a topological space and a quotient map. In other words, an onto map. So y is the quotient space of x, and y has the quotient topology. Okay, so a subset here is open if and only if its inverse image is open, and I have another space and a function from x to z, and I wonder whether there is a map like this. Okay, well, we know that there is such a map H if and only if uh, G is constant on each equivalence class. In other words, on the fibers of uh, this quotient map. So what is the fiber? So what is the subset above this point, right? This is a point in Y. The subset above this, so this is just actually f inverse of this point again, right? F inverse of this. Here I regard this as a point. Here I regard this as a subset, right? Okay, so if G is constant on the subset, in other words, if G sends every element of this subset to a single element, then we know that there is such H. This theorem tells us that there is such an H, and that H is also continuous, provided that G is continuous. Actually, continuity of G is equal to the continuity of H. And the proof is very simple. So we know that H exists if and only if G is constant on each equivalence class, EA fibers of F. And so I have to prove the following. H is continuous if and only if G is continuous. First, assume that G is continuous. Okay. Well, must show H is continuous. How can we show this? Well, let H is from where to where? H is from Y to Z. So let U be an open subset. Then what is G inverse of U? G inverse of U, G is equal to H composition F, right? And this is equal to what? Well, if you take inverse image of a composition, that is the inverse image of uh, U under uh, H, and then you take inverse image under F, right? You switch the order. Well, we have this, and what we know is that we assume that G is continuous. So by assumption, G is continuous, and thus G inverse of U is open in X. But then let's see what we have. I have this set, and its inverse image under F is open in X, right? Because it is equal to this one, and this set is open in X. Since Y has the quotient topology, then this set must be open. Since Y has the quotient topology, H inverse of U must be open in X. But let's see what we have. I started with an open set in Z, right? Open subset. And we saw that its inverse image is open in X. This means H is continuous, right? So H is continuous. Hence, H from Y to Z is continuous. The other direction is also obvious. Why is that? This time I will assume H is continuous. Well, then this will be open. But since F is open, this composition will be open. Therefore, G inverse of U will be open. Therefore, G will be continuous. Okay. The other direction is proved the same way also. Okay, so I stop here. Okay. All right, let's see some examples. Okay. Okay. Let S2 denote the unit sphere in R3. Okay. So S2 is this X, Y, Z in R3, so that X square y square z square equals 1. Okay. All right. Okay, so a cube S2 with the subspace topology uh, inherited from R3. Okay. Uh, consider an equivalence relation on uh, S2 uh, defined as follows. So 2 points x1, y1, z1 and x2, y2, z2 on the spheres are said to be related, equivalent, if and only if uh, one of them is the minus the other one. So x2 z2 is equal to minus x1 y1 z1. Okay, maybe I should say plus minus because every point is equivalent to itself, right? So this means what? I see antipodal points as the same. Okay, so I have a point here x, let's say y z, and it's antipodal. So you go like this point minus x minus y minus z. So it is on the back side of the sphere. Okay, if this point is on the northern hemisphere, then this is in the southern south hemisphere. If this is on the east, then this is on the west. Okay, so we regard such points to be the same. Well, let okay, since this is an equivalence relation, I can consider the quotient space. The quotient of S2 by this equivalence relation is called the real projective plane, denoted as RP2. So what is this RP2? Real projective plane. Plane means it is two-dimensional, so it is nothing but the sphere. I mod out the sphere by this equivalence relation. In other words, I identify antipodal points. Okay. Well, what kind of object is this? Okay. Can we draw a picture of RP2? Okay. We can draw the sphere, right? I did. Here is the sphere. So can we do the same for RP2? Let's see. Drawing a picture means you have to draw an object so that every point on the object should correspond to a unique point on the you know of that set, right? So there should be a one-to-one correspondence between the object and its image. In the sphere, right? Every point of the RP2 has 2 points, right? X, Y, Z and minus X, minus Y, minus Z represent the same point on RP2. So this is not a picture of RP2. To get a picture of RP2, I have to delete half of the sphere, right? So I have to do this. Get rid of the southern hemisphere. Okay. So that almost all the points now in RP2 has a unique representative, right? A unique representative, which is on the northern hemisphere. But not exactly. Why is that? Because still there are points here, like this one. This XYZ on the equator is still identified with this point, minus X, minus Y, minus Z, and they are, distinct points on this half sphere. So I have to identify also these points. I have to identify this point with this one and this point with this one and so on, right? So this thing is a bit complicated, not something actually done easily. Let me draw another model. Suppose you press this sphere and you make it a disk. What you do, you identify antipodal points on the circle. So you identify this point with this one, this point with this one, and so on. You have to do this. In other words, you have to just glue half this boundary, let's say, with the other half, but you have to glue it this way. So this point is glued to this one, this point is glued to this one. You may try to do this, take a piece of cloth, for example, and try to do this at home, but you will not be able to do that. It has to cross it itself, okay? The reason is that RP2 okay. So fact is this is not an easy fact. If you can do this, in R3, it means you have a copy of RP2, real projective plane, in R3. In other words, there is an embedding of RP2 into R3, but that's not true. The fact is that there is no embedding, topological embedding of embedding, let's say H from RP2 into R3. Okay. Proof of this requires algebraic topology or there is another way, or intersection theory. Okay, intersection theory. So these are kind of, graduate level stuff. But I have a video on my page which explains all this. Okay, you may look at that one. It's about, I guess, drawing rectangles on curves. Okay, whenever you have a curve in R2, you can always find 4 points on this curve. Well, okay. It may not be easy, of course. Yani bu durumda pek de kolay gibi gözükmüyor. Okay, maybe like this. So that this is a rectangle. So on each curve, you can always find 4 points so that those 4 points are corners of a rectangle. This fact is equal to the fact that RP2 cannot be embedded inside RP2. Sorry, R3. Okay, so the fact I just actually mentioned here. But as I said, the proof is, a little bit too much for our course for the time being. However, so RP2 doesn't live in R3. Değil mi? Biz Türkçe'de ne diyoruz? Hani RP2'yu R3'ün içine gömemiyoruz. RP2'nun R3 içinde yatacak yeri yok. Ama R4'e veya R5'e yapabiliriz. Another fact, RP2, so there is an embedding H from RP2 into R even R4. Okay, and proof this is not very difficult. First, let us construct an embedding into R5. How can we do this? Well, we will do it this way. So you see, I have I have S2 here, right? And I have RP2 here. And I need to find an H into, say, R5. Okay, R5. Well, this map should satisfy what? This map should be constant on the okay, let's say equivalence class of this relation. So R denoted like this. So this is x, y, z, and minus x, minus y, minus z. Okay, so these are so-called homogeneous coordinates. It represents this subset x, y, z, and minus x, y, z, minus x, minus y, minus z. So these are the points in the projective plane, and above this projection map, I have this subset x, y, z. This is a subset here. This is a point here. This is my quotient map, sending a point xyz to its equivalence class. Okay, I want a map like this. Well, for if there is a map, of course, then this composition gives me a map like this. And this G from S2 to R5 should be constant on each equivalence class, right? Should be constant. If there is an H like this, G should be constant on each equivalence class. This means what? This means, in other words, G of x, y, z must be G of minus x minus y minus z for all x, y, z on the sphere, of course. Well, this means kind of, the components of G must be even functions, right? So replacing minus x, x, y, z with minus x minus y minus z shouldn't change anything. Do we know such functions? I mean, which satisfies this? Well, of course we have, right? For example, x squared is such a function. If you replace x with minus x, nothing changes. Y squared, z squared, xy, xz, and yz, right? All second order polynomials are like this. So I may use this guys to define G. Indeed, just let G from S2 to R5 given like this x, y, z. Let's take these functions x squared, y squared. I skip z squared. Why is that? Because x squared, y squared, z squared is already 1. So if you have x squared and y squared, you have already z squared, which is 1 minus the first two coordinates. So there is no reason to write z squared here. Instead, let me just write the other three components. So I have 5 elements here, monomials, and okay, so let G to be S2 to R5 given by X, Y ya da kalsın, tamam. Böyle kalsın. Peki. Şimdi tabii ki clearly, right, G x minus y minus z is the same as x, y, z. Well, in other words, G is constant on the fibers. Hence, so since G is constant on each equivalence class, there is H from RP2, which is just S2 divided by this equivalence class into R5. Okay. Moreover, since G is continuous, why is that? Well, you see, G as a function from R3, right? I may consider this function from R3 to R5. Its coordinate functions are all continuous, right? Therefore, G is continuous. And this G is nothing but the restriction of this function to its subspace, which is S2. Therefore, this function is also continuous. And since this is continuous, H is automatically continuous. Since G is continuous, H from RP2, okay, RP2 into R5 is continuous. Nasıl tarifli bu? Tabii ki şöyle. H'in herhangi bir denklik sınıfındaki değeri nedir? G'nin x, y, z'deki değeri. X, y, z'deki değeri is continuous. Okay. So I have a map, continuous map from RP2 into R5. I will leave it as an exercise that H is 1-to-1. This is easy to check, okay? H is a 1-to-1 map. G is not 1-to-1. G is 2-to-1. So this G is 2-to-1. It sends 2 points to 1 point, right? It sends X, Y, Z, and it's negative to the same point. So this is a 2-to-1 map. We represent it like this, 2-to-1 map. But H is 1-to-1 because these 2 points are identified here, so they become 1 point. Therefore, this H becomes 1-to-1 map. 1-to-1 map, and it is continuous. Is it enough for H to be an embedding? Not necessarily, right? Not every 1-to-1 continuous map is an embedding. You need more, but for that we need some more material. We will see later that since RP2 is a compact space, compact Hausdorff space, H is a homeomorphism onto its image. In other words, H is an embedding, topological embedding. But we need to cover this compactness stuff. So I'll come back to this example later. But as another exercise, you may show this. So RP2 with its quotient topology, is Hausdorff. Okay, it's actually very simple. So whenever you have 2 points, you have to find open sets containing these 2 points, and these open sets should be disjoint. Okay, maybe I can do this. Yeah, take 2 points, P and Q. Let's say equivalence class of P and equivalence class of Q. They are different. Well, so on RP2, I have these points. On the sphere, they correspond to what? So this P is something like this. P is here, and I have minus P here, right? And we have Q. Q is different than P, so its equivalence class is different. So Q is somewhere here, and minus Q here. Now I have to find open sets around Q and P so that this open set should be disjoint. Well, I will choose V like this, and U like this. right? They will be disjoint if I choose this open sets small enough. In other words, on the sphere, I have 4 points, which are actually antipodal pairs, right? Two antipodal pairs. Since they are distinct, I can choose small balls around these points, which are all disjoint. And I choose this ball so that when I multiply one of them with -1, I get the other ball. Okay, so I multiply all the points in one ball, I get the points in the other copy of ball. So the balls around P and minus P are uh, what? One of them is obtained from the other one by multiplying -1. And the same thing for the blue balls. Since on the sphere they can be chosen disjoint, their images under the projection map in RP2 will be disjoint. These are open sets because their inverse images are open. And since their inverse images are disjoint, this U and V are disjoint. Okay, so RP2 is really Hausdorff. Okay. Well, consider another example. Let's say x is the interval 0 to 2 pi, considered as the subspace of R standard. Okay, and let uh, uh, let us consider the following equivalence relation. Uh, define on x as follows. Uh, x and y in x are related if and only if x and y are elements of 0 and 2 pi. So this means 0 is equivalent to itself, 2 pi is equivalent to itself, or 0 and 2 pi are equivalent to itself. In other words, I just identify the two ends of this interval, right? I just identify the two ends of this interval. Well, what would you get if you identify two ends of this interval? Of course, you get a circle, right? So 0 and 2 pi are identified. You just get a circle. What are the open sets of this quotient space? Well, uh, so this is my x. Here I have x over this. What are the open sets? So here I just identify the two ends, right? Okay, let me just draw like this, but keep in mind that these 2 points are identified. Now, what are the open sets here? You see, a set is open if and only if its inverse image is open, right? So if you choose an open set like this, its inverse image is like this. So if you choose an subset like this, this will be open if and only if its inverse image is open. So if you choose this U above an open interval, then this will be open. What about intervals containing the endpoints? Well, if you choose an interval like this, will it be open? What is the inverse image of this? Inverse image of this is this, right? But you see, this point and this point are identified, and if this belongs to the open set, then in the inverse image this point is should be belong to the open set. But on the standard topology of R, if you have a point like this belonging to an open set, then an interval containing this point should belong to that open set. So my open set cannot consist of a single half interval like this. It should contain both intervals. Therefore, an interval, an interval, or an open set containing this point should contain actually uh, should have two pieces, right? Because these 2 points are the same, and therefore uh, an interval containing 0 should have both a piece containing 0 and a piece containing 2 pi. Okay, and here they correspond to something like this. This open set, you the blue one is like this, and the red one is like this. Okay, well, how can we say that this quotient space is really the circle? So here is my claim. X divided by this subset is homeomorphic to the circle S1 in R3 in R2. So this is, let's say, circle. So what we mean by the circle, I mean xy in R2. So it has the subspace topology x squared plus y squared equals 1. Well, I have to find the homeomorphism. Uh, how we do this? Well, here is my, g from the interval 0 to 2 pi, 0 to 2 pi into uh, S1 given by gt is just cosine t sine t. Okay. Well, this function is one-to-one everywhere except the ends, right? 0 and 2 pi are mapped to the same point, but besides that, it is one-to-one. And actually, so if I let this function to be g is clearly continuous, right? This is just sine and cosine, so it is continuous. And here I have my x over delta. So what is this? It is the interval 0 to 2 pi where the points 0 and 2 pi are identified. Since they are identified, this is my quotient map F, sending a point to its image in the quotient space or the equivalence class containing that point. We know that G is constant on the fibers of F because each equivalence class here contains only one point. Therefore, G is constant on a one-point set. The only thing we have to check, the equivalence class of 0. Equivalence class of 0 has 2 points, 0 and 2 pi, and 0 and 2 pi are mapped to the same point. So since G0 equals G2 pi, h from x over tilde to S1 exists, and it is continuous. So there is H, and H is continuous because G is continuous. Okay, and this H is 1 to 1. Why is that? Well, the only 2 points which violates one-to-oneness right above for G were the points 0 and 2 pi, and I just identified those 2 points. Now they became 1 point. Therefore, this G became 1 to 1. Okay. So clearly, H is 1 to 1. So H is a 1 to 1 and onto mapping. Hence, H is clearly continuous and onto, right? Hence, okay, uh, so H is a one-to-one onto and continuous mapping. Again, we will see later that by the compactness of X over tilde, well, actually this set is compact, therefore its image is a compact space, compact and Hausdorff. Therefore, a one-to-one and onto continuous map has to be a homeomorphism. Since X over tilde is compact, so we will see this argument later. H is a homeomorphism. It's compact and Hausdorff, maybe I should say. I am not sure whether we need Hausdorffness, but probably Hausdorff. H is a homeomorphism. So we will see the reason why this homeomorphism later, but that's the fact. Okay. Evet. Ara verelim. Aradan sonra devam ederiz.